Have you ever noticed how a rotating helicopter blade in a video sometimes seems to stand still or even spin backward? That intriguing visual illusion is a perfect analogy for what happens in digital signal processing when the sampling rate falls below the Nyquist rate. The direct answer is that you encounter a phenomenon called aliasing, where high-frequency components of the original signal masquerade as lower frequencies in the sampled digital signal, leading to irreversible data corruption. The core reason this occurs lies in the fundamental principle of the Nyquist-Shannon sampling theorem, which dictates the minimum sampling rate required to perfectly reconstruct a continuous signal. This theorem states that a continuous signal must be sampled at a rate greater than twice its highest frequency component to avoid losing information. When you sample a signal at a rate lower than this critical threshold, multiple distinct high frequencies can appear identical to lower frequencies after the sampling process. Imagine trying to capture a very fast-moving object with a camera that takes pictures too slowly. You miss key moments, and the object's path becomes distorted or even appears to move differently than it actually does. This distortion is precisely what aliasing represents, making it impossible to recover the original signal truthfully. To prevent this detrimental effect, engineers employ several practical strategies. The most crucial step is to use an anti-aliasing filter, which is a low-pass filter applied to the analog signal before it is converted to digital. This filter effectively removes any frequency components higher than half of your chosen sampling rate, ensuring that the digital conversion process only sees frequencies that can be accurately represented. Another key aspect is carefully selecting a sufficiently high sampling rate based on the known or estimated bandwidth of the analog signal you are working with. By doing so, you create a digital representation that faithfully captures the nuances of the original analog input. This crucial boundary is often referred to as the Nyquist frequency, which is precisely half of the sampling rate. Any signal components above this folding frequency will be incorrectly interpreted as lower frequencies and folded back into the usable frequency band. Understanding and respecting this limit is not just an academic exercise. It is fundamental to the integrity of countless digital systems, from audio recording and playback to medical imaging and telecommunications. It ensures that the digital data accurately reflects the original analog information, allowing for precise analysis and reliable reconstruction. Therefore, adhering to the Nyquist criterion is paramount for anyone working with analog to digital conversion. It safeguards against the introduction of spurious low-frequency components that do not exist in the original signal, which would lead to incorrect interpretations and flawed data. Proper sampling ensures the accurate capture and reliable processing of information, serving as the bedrock for all effective digital signal processing applications.